Boys and girls, put down that roll of PETG because in this video, we're testing out 17 functional, special purpose 3D printer filaments to level up your next project. I'll tell you what they're for, why they're special, and what it's like to print them so that you can decide whether or not they're worth your money. And stick around till the end because I'm saving some really exciting new filament brands and types that I've never gotten my hands on before. Let's get after it. Over the last few years, flexible filaments have matured from a limited use novelty to a wide range of specialized filaments for a variety of real-world applications. So let's start the list off with some purpose-built flexibles to level up your next project. First, the filament that actually inspired this entire video idea, the GRIP series by Polish filament manufacturer Noctuo. Have you ever had a project or application where you needed traction or grip? Perhaps you tried the standard TPUs and even PBAs only to find that they were as slippery as a politician. A lot of these newer air or foaming TPUs that I covered in the last video in the series are better in this regard, but I still wouldn't rely on them in an application where grip is imperative. Enter GRIP, a purpose-built flexible filament designed for, well, grip. Now, to my knowledge, this is one of the only commercially available FDM filaments to exhibit this unique property. But how does it actually print? After all, if it's so grippy, will it actually slide through PTFE tubes, extruder gears, or heat breaks? To be honest, printing this stuff was surprisingly easy. I did bypass the PTFE tube on the Prusa XL, but I was able to print it without any issue on the Core 1 without even using the filament sensor bypass. However, it did do something that I've never seen any flexible filament do before. It detached from the PEI build surface on two separate printers. But switching to a clean satin build surface did eliminate that issue, and from there, it just printed like normal TPU. First impression, the material is more ductile and pliant than I was expecting, and because it's matte, you can clearly see that it is not normal TPU. With that said, it wasn't quite as grippy as I was expecting it to be. So I decided to test it out by modeling up this non-slip sleeve for my filament spool holders and then dragging it using a force gauge. And the results were a mixed bag. In my first tests, it outperformed normal 95A TPU, but it actually underperformed some 80A PBA. And none of them came even close to the store-bought anti-slip fabric. But when I loaded on more weight, the grip did outperform the PBA. I need to do a lot more testing on this, but from my initial results, it seems that while grip easily outperforms the standard 95A TPU that we're all used to, its performance is going to depend on which surface it is measured against and how much pressure is applied to it. In-depth testing for any one filament is outside the scope of this video, but do drop a comment below if you'd like to see me cover this more in a future one. Up next, we're gonna take a look at the ROAMR series of TPUs by Siraya, designed specifically for 3D printing shoes. But I covered a specialty shoe printing filament like the BQ Moreflex, as well as Siraya-Tech's TPU and PBA Air in the last installment of the series. So how is this ROAMR any different? Well, according to Siraya, they developed the ROAMR series to find a happy middle ground between performance and comfort. So think more rebound than a TPU Air without feeling like you're walking on a trampoline like you would with PBA or PBA Air, and hopefully less irritation and chafing on skin as well. It also comes in a range of different hardnesses, including 80 and 85A. Now, to test this one out, I 3D printed a new wide version of my favorite 3D printed shoe design, the Waveform by Alessio and Stepan. But right from the beginning, I saw that it was printing too fast and extruding too little with the recommended settings, probably because I didn't slow down my print profiles nearly enough. Now, this is something that will come up multiple times throughout this video. It really seems like these foaming filaments don't just need space to actually foam, but they also need a lot of time, which means printing painfully slowly. Now I did adjust the extrusion up to 115% and slow the print speed down to 50%, and that yielded a satisfactory result. But unfortunately, as you can see, the back of the shoe did tear the second time I went to put it on, but that actually has happened to me before a lot of times when printing this particular design with anything but your normal TPU. Now, as for the material itself, I definitely like it more than the Moreflex that I used in a previous video. It has more of a foamy feel and less of a rubbery one. But the skin feel, at least on these types of infill-only designs, still isn't nice enough to go without socks. But above all, I personally don't like just how squishy these are with such a thick sole. You might like it, but personally, as a barefoot guy, I'm gonna try and print a much more barefoot style shoe and see how it holds up with this filament. By the way, for each of these filaments, we will go ahead and leave links in the description, some of which do support the channel should you choose to pick them up. And we really appreciate you using our links. It helps us make videos like these. All right, for our next three categories, let's get elemental and break them down by earth, wind, and fire, starting with earth. You may know that while PLA is made from natural materials like sugarcane or corn, it unfortunately does not break down in the soil or home composting setups. So what if you need to 3D print something that will break down in any biotope without leaving behind microplastics? You know, like a lattice structure for supporting plants or aquatic life or something like that. Well, in that case, what you're looking for is ColorFabb's AllPHA PHA filament. Made of polyhydroxyalkanoates. It's 100% bio-based and 100% biodegradable, allowing bacteria to actually feed off of it and break it down via fermentation. Now, the rate of breakdown is going to depend on the environment, of course, but you can control that rate of breakdown by varying the number of perimeters in your print, which is actually really cool. But is it as friendly to our 3D printers as it is to the environment? To test that out, I tried printing a variety of plant paraphernalia, including some trellises and some support spikes. ColorFabb does note on their website that bed adhesion can be a problem, and they recommend a cold plate plus 3D lac. Now with that combination, I did have the best success, but the print did slowly peel off the bed, and as you can see, the longer, taller parts ultimately did fail. Now, if I were to try printing this again, I'd probably want to first experiment with all the different types of Magigoo to see which one of those stick best. As far as actually printing it, I did have to disable auto retract on the Prusa printers because the soft texture of this stuff caused the jam immediately after loading. But other than that, it honestly printed just like normal PLA if PLA didn't stick to your build plate. One weird thing worth noting though is that this stuff absolutely stinks when printing it. It kind of smells like old Cheetos that have turned. So my verdict, well, like many of the filaments on this list, I probably wouldn't choose to use this filament unless I actually needed it for a specific use case. But as a lifelong tree hugger, I'm certainly glad that it exists. And it makes me really happy to think about marine biologists or agronomists using 3D printing to restore natural habitats. So that's a great filament for all things Earth, but what if you're looking to fly with the wind? Well, in that case, you'll want to take a look at these high-flying specialty filaments. First, we have LW-PLA, or lightweight PLA, which is available from brands like Polymaker, ColorFabb, and eSun. Now, the idea here is actually really simple. You take those same types of foaming agents used in things like TPU air, and you add them to plain old PLA. Why would you do that? Because by doing so, you replace somewhere between 30 and 65% of the material with air bubbles, and therefore you reduce the weight accordingly. This makes LW-PLA perfect for gliders and all sorts of airborne applications. But there are actually plenty of applications where you need the weight to be as minimal as possible. Things like sensor components, cosplay armor, cases for things that are gonna go in your hiking gear. But all that weight savings, has to come at a cost. And it left me wondering whether the resulting parts from this material are still strong enough for the structural components of things like drones or RC planes. To test this filament out, I created my own quick and dirty profile based on the higher end of ColorFabb's recommendations. For the optimal results, I would definitely need to do proper calibration and tuning, but for obvious reasons, I don't have enough time this week. In any case, for this particular filament, I set up a full build plate with parts that offer both qualitative and quantitative comparisons. Now here, once again, it seems like you really do need to allow sufficient time for the material to foam and exit the nozzle, because I quickly realized that I would have to slow things down even further to, I think, like 50%, and I still got a lot of stringing, but like I said, I'm sure that that is something that I could dial in if I had the time to properly calibrate my profiles. But the results are nonetheless pretty interesting. Like, you know that the print is going to be very, very light, but you're still very surprised when you pick it up. In fact, as you'll see in a second with the ASA, the tensile strength samples are actually so incredibly light that I had to switch to a more precise scale just to measure them. And if you're wondering what this stuff feels like in person, it really reminds me of like a styrofoam or a balsa wood, which makes sense. Now for my testing, these are indeed about 40% lighter. But as you can see from the chart, they're also significantly weaker. So that's all well and good, but there's just one big problem. PLA is notoriously susceptible to heat. Simply leaving it in the hot sun is enough to cause deformation, and you can only imagine what something like a hot drone motor would do to it. It's a real Icarus situation. Enter lightweight ASA, available from two European companies that are actually new to the channel, ColorFabb and Spectrum Filaments. Lightweight ASA takes that same foaming technology for which ColorFabb is well known by now and adds it to a more serious engineering grade thermoplastic. The result? A 60% weight reduction while maintaining high UV resistance and the ability to withstand up to 96 degrees Celsius. Here, again, I had to slow the profiles down quite a bit, and as with the lightweight PLA, I still did have a ton of stringing on these untuned profiles. As you can see, the weight savings are, again, as advertised, but again, the strength is compromised accordingly. But what if you've set your sights even further than that, like beyond Earth's atmosphere far? We're talking like DIY satellites similar to the one launched by YouTuber Mark Rober. For that, you're gonna need a space-grade material. Fortunately, the folks over in Prague have you covered with their PC space-grade material. Now, what makes it space-grade, you ask? Well, for starters, it's ESD safe. No short circuits rendering your payload dead on arrival. What's more, it has particularly low outgassing, even in the vacuum of space, which apparently is something that normally is only available with much, much more expensive polymers like PEC and PEEK. Add that to the usual high temperature resistance of PCCF, which this is, and you get a material that is both affordable and able to endure the harsh vagaries of space travel. Just don't forget your towel. Now that we've covered earth and wind, let's switch over to fire with some filaments that are designed to interact with fire in various interesting ways. First, we have this flame retardant ABS V0 by Noctuo. To be clear, flame retardant filaments are nothing new, and I've even covered some exotic polymers like PPS that are flame retardant by nature before in this series. But this is the first time that I've ever tested out a commodity plastic like ABS that has been modified to be extremely flame retardant. In fact, it's actually UL94 V0 certified. I suppose the idea here is to allow you to swap your existing ABS-centric workflow and designs to ABS V0 rather than to another polymer altogether, which may have different shrinkage rates, different protocols for handling it, or different mechanical properties. So I was very happy to see that this stuff prints absolutely perfectly with just normal ABS profiles. One interesting thing though is that it smells completely different from ABS. So none of the typical styrene fumes that you might be familiar with, and much more like some kind of health clinic or dentist's office or something like that. So here I have the same specific part printed in Siraya high temp ABS and Noctuo's ABS V0. And of course, super powerful fume extractor is on hand. So let's go ahead and see how these two different filaments burn, baby, burn. Obviously, flame retardance is another one of those super specific use cases, but if this demonstration has proven anything, it's that you really shouldn't risk it with standard materials in any application where there's any risk of flames. And with more and more of us experimenting with high temperature materials and chamber heaters for everything from Vorons to Bamboo Lab machines, it's good to know that we have a one-to-one replacement for the ABS that many of our projects are already based on. So that's great if you don't want your prints to burn, but sometimes you actually want the exact opposite, a polymer that burns as cleanly and easily as possible. I'm talking, of course, about loss casting for metal parts. Enter Polymaker's PolyCast, a filament designed not just to melt well, but to burn away cleanly when you're done with it. This, in turn, allows you to create complex and strong cast metal parts much faster and cheaper than traditional methods, and at a fraction of the cost. Now, unfortunately, I don't have a crucible here in the studio to test it out and demonstrate with this filament. I really kind of don't trust myself with something like that, given my optimistic relationship to safety protocols. But if you are interested in seeing me experiment with casting from 3D prints, do drop a comment down below, and maybe I'll pick up some of the gear and try to do a video where I experiment with it. Maybe. So at this point in the video, you might be thinking to yourself, Jonathan, carbon fiber, PC, and ABS with all sorts of fumes, I just don't have a printer that's rugged enough and capable enough to handle those kinds of filaments. But if that's the case, then I highly recommend that you check out the 3D printers from this video's sponsor, Prusa Research. They're designed to be rugged and last a lifetime, with upgrade kits to allow you to upgrade to the latest model, and they're infinitely upgradable because they're open source, and also because Prusa offers affordable, high-quality upgrades like air filters, hardened nozzles, the very exciting upcoming 450°C nozzle upgrade, and even the index upgrade that's going to allow you to print with up to 8 colors and 0 waste. So to check out Prusa Research, visit the link in the description. Thanks, Prusa. Now let's get back to the video. How do I get down? When it comes to 3D printing, resistance is anything but futile. In fact, we have a wide range of filaments at our disposal designed to resist all sorts of things, from chemicals to radiation, depending on your needs. First off, a completely new filament type for the channel, HDPE, or high-density polyethylene. Now, up until now, HDPE has been considered extremely difficult to 3D print. But according to the manufacturer of this roll, Spectrum Filaments, they are among the first to create an innovative, low-warping version of HDPE that you can actually print. I'll be the judge of that in just a minute. But first, why bother? With so many great filaments out there to choose from, why do we need another thermoplastic? Well, if you look around you in your daily life, you will realize very quickly that polyethylene is one of the heavy hitters among thermoplastics, and there's a reason that it's used for such a wide variety of things. First, and perhaps foremost, it has class-leading, exceptional resistance to acids, bases, oils, and even solvents, which is why those bottles of acetone, bleach, alcohol, and so on in your cabinet are made of it.
What kind of plastic, man?
Polyethylene.
But beyond that, HDPE also has exceptional wear and crack resistance, low moisture absorption, and even high heat resistance. It's even UV stable and non-flammable. This stuff is like the cockroach of thermoplastics. Almost nothing will kill it. And yet, when I took it off the build plate, I was still surprised at just how hard it was to remove the brim. This stuff is tough, and it's actually much more rigid than I was expecting, but I guess that's the difference between HDPE and the low-density polyethylene that we're so used to from our daily lives. As promised by Spectrum Filaments, I had absolutely no problems printing it, although I did cheat a little bit and use the PP plate from Prusa to improve bed adhesion. I'll be honest, I wasn't quite sure what to print with this stuff, so I just printed this Gridfinity bottle that I can use to put acetone or rubbing alcohol in. And I would love to know in the comments below what you would print with this material, because I am really itching to experiment with it a whole lot more. Similar to HDPE is polypropylene, or PP. And no, I'm sorry, I'm not gonna make any PP jokes. But if HDPE is the cockroach of thermoplastics, then PP is more like an axolotl, or some other kind of slippery, chemical-resistant cousin that just refuses to die. This stuff is tough. Like HDPE, it shrugs off a ridiculous range of acids as well as bases. It barely absorbs moisture, and on top of all of that, it has fantastic fatigue resistance, meaning parts that you flex, snap, and abuse over and over again are exactly where PP starts to make a whole lot of sense. So why have we all mostly been using polymers like TPU or even nylon in those types of applications? Well, because PP has two personality traits that make it a nightmare. First, it loves to warp. And second, it absolutely hates sticking to most build surfaces. In fact, polypropylene is so notoriously picky about what it sticks to that up until recently, the best way to print it has just been to cover your build plate in polypropylene-based packing tape. Yeah, not pretty, but no more. PP has gotten way more accessible lately. First, this video's sponsor, Prusa, actually sells polypropylene build plates, which make it much easier. And if you don't have a PP plate, there are now specialized adhesives like Magigoo PP, which work with a wide range of surfaces by giving PP something that it actually wants to bond to. So for this test, I printed a funnel and another Gridfinity bottle for some solvents and a living hinge sample to help me demonstrate PP's legendary ability to withstand abuse. I also did experiment with printing a couple vase mode bottles, but I didn't have a ton of success just due to the overhang performance. I have to say that polypropylene was very different from what I was expecting based on the descriptions that I'd read. Thick parts are incredibly rigid, but thin parts are incredibly flexible, but not in a springy way like TPU. I've definitely never printed anything that is so down the middle between rigidity and flexibility. This stuff is really, really cool. And here again, I would love all of your suggestions for what I should try printing with it next. So that's got you covered when it comes to acids, bases, and solvents. But what about radiation? Sure, your exotic, high-end plastics like PEI and PEEK can resist things like ionizing radiation and X-rays pretty well, but they aren't gonna protect you from it. Instead, for that, you're gonna need a heavy metal. And try as I might, I couldn't find any filament with lead in it. I wonder why. So instead, the go-to for these types of applications is tungsten. And thankfully, Prusa makes their very own Prusament PETG-Tungsten. Designed for use in laboratory and medical environments that require functional radiation shielding, it has the benefit of being hypoallergenic and non-toxic. Unfortunately, tungsten powder ain't cheap, and so neither is this filament. I was honestly too shy to beg for a sample of this stuff during my recent tour of Prusa's HQ, so instead, you get a Benchy. And you guys better appreciate it, because the way that this thing lit up on the X-ray machine at the Prague airport brought me the closest I have ever been to a full-on strip search. All right, we've covered chemical resistance, radiation, but what about heat and general abuse? Yes, we've covered some extremely high temperature filaments like PPA-CF before, but those materials can be expensive, abrasive, and very hard to print on consumer 3D printers. For this reason, Polymaker developed their Polyamide CoPA, a copolymer of nylon 6 and nylon 6.6 that combines high tensile strength properties, heat resistance up to 180 degrees Celsius, and the extreme toughness that nylon is known for. Best of all, it's the only nylon I've ever encountered that can be printed on an open printer, making it much more accessible to a wider range of people. Now this stuff is great for any application that's going to see repeated impacts, mechanical strain, or sustained heat. To put the printability of this filament to the test, I chose some models that should be seriously difficult in a filament that is prone to warping and adhesion issues, even in an enclosed printer. My main objective was to test to see if this filament actually could be printed on an open printer. So I chose to print it on my Prusa XL. But just to give the filament a fighting chance, I did load it up in a dry box and I swapped over to Prusa's nylon plate. And I just walked away. Now, to my absolute amazement, the print completed absolutely without a hitch. In fact, I even had to pry the parts off the build plate. Now, I'm not sure how much credit is due to the filament versus the dedicated build plate, but that's seriously impressive. So I decided to push my luck and I tried printing a very tall, detailed PTFE tube guide for a high temp printer project that I'm working on. And that printed without a hitch too, albeit a little bit of stringing. Here again, the finished parts really surprised me. When I think of nylon, I think of this kind of slippery, self-lubricating filament that absorbs impact. But this stuff is incredibly rigid. It almost feels like polycarbonate. Now that might be because I printed with lots of perimeters, or it might be because the chemistry that's responsible for its superior printability changes it. But either way, I'm seriously impressed by the results. And this is a filament that I am definitely going to be using a whole lot more around the studio. But if you need the most extreme impact resistance, there's simply nothing like TPU. Its superior layer adhesion and ability to absorb abuse are legendary among thermopolymers, but it's also a little bit flexible. And that's why Siraya Tech recently added glass fibers to it in their Fibreheart TPU-GF, adding rigidity and stiffness to the mix. The result is a filament that truly borders on indestructible, and which some say is poised to revolutionize the combat robot space. I'm sure there are a lot of really cool applications for this, but first, how does it print? Well, to test this one, I wanted to print something that really does need to be indestructible. And so I printed some replacement parts for the Death Racer that I built with my son a while back, because he keeps crashing it and destroying the ASA parts. The parts printed beautifully for the most part, and no surprise, I really love this textured matte finish. But there was one thing that really did surprise me. See, even with the glass fibers, this stuff is actually very flexible, especially where the part is thin. Now don't get me wrong, the thicker parts are definitely much more rigid than normal TPU, but as you can see, these thin parts here were so flexible that they actually moved under the print head during printing, causing local layer shifts. Now because of this, you will want to account for this level of flexibility both in the design phase, when you think about how thick perimeters should be, and when slicing. But before I hand these over to my son for some real-world testing on his Death Racer, here's some gratuitous durability testing for all of you. And now let's talk about the supporting cast. Filaments that were put on this earth to support the stars of the show. First, we have these common support for PLA materials. First popularized by Bamboo Lab, they're now available from some other companies, including Snapmaker and Polymaker. The idea is that these are easy to break away from PLA. Personally, I don't really like this stuff. I find that it tends to unravel and have terrible layer adhesion, making it a nightmare to clean off of your parts. Honestly, I find that you're better off using PETG for most types of prints if you want to use a separate support material. Now, I say most types of prints because there are some situations where you might need something a little bit more. That could be extremely complex geometry, tight spaces that would be hard to access, or needing to place supports where you just cannot accept scarring or artifacts. Now in situations like those, your best bet is going to be PVA. Yes, PVA, aka polyvinyl alcohol, the same stuff as your common glue stick. Now, this is not to be confused with the other PVA, polyvinyl acetate, which very confusingly is what wood glue is made of. One helps woodworkers hide their shame, the other dissolves in water. Now this is useful because it allows us to support our trickier 3D prints however we want and let water, which is notorious for getting into tight spaces, remove those supports for us after the fact. So why not use this stuff for everything? Well, for one, it's weird. Because it's reactive to water, it is extremely susceptible to humidity and stringing while printing. What's more, in my experience, it's pretty gummy, at least in my humid environment, which means it won't perfectly support your objects the way a rigid support material would. It's also more expensive than just supporting your print with the same material, if possible, that is. And finally, I find it just really yucky. Still, if you need it, you need it, and I've seen people do some really cool things that simply wouldn't be possible without PVA. Up next, we have PolySupport PA, which, as the name suggests, is a specialized support filament for polyamide, or nylons, predominantly nylon 12. But I know you're wondering, why does nylon get its own support material, whereas other materials like ABS or PETG don't? Well, put simply, nylon's a bit of a diva. It prints hot, often in a heated chamber, and it loves to warp. So you run the risk of either bonding the print to the supports if the bond is too good, or if it's not good enough, the print actually warping away from the supports. And when you're printing large functional parts out of very expensive carbon fiber nylons, you really don't want to lose the entire print because you failed to achieve that Goldilocks level of support adhesion. Also, while PolySupport PA isn't cheap at $39.99 for half a kilo, it's still about 40% cheaper than printing your supports out of PA12CF, so that's nice. And now we've arrived to the deep end, the funky, functional, and specialized filaments that just don't play by your rules, or fit into any of my other categories. First, we have ABS Kevlar, like this spool from Spectrum Filaments. It's like ABS carbon fiber, but with Kevlar, because Kevlar is cool, Jack. But in all seriousness, ABS Kevlar is a bit different and better for different applications. Whereas ABS carbon fiber can be very rigid, but also somewhat brittle, its Kevlar reinforced counterpart has a little bit more give, and therefore can withstand impacts a little bit better. It's also, I found out, a bit less abrasive than carbon fiber, both on your nozzle and on your skin. Plus, while it doesn't improve warping as much as carbon fiber, adding Kevlar still does make ABS less warp prone and more dimensionally stable. And finally, let's end on a bit of fun with this new PETG Ultra-Glow from Prusament. I know, there have been plenty of glow-in-the-dark filaments on the market for years, but none of them were bright enough to serve any kind of functional, mission-critical, or emergency purpose. But this one is. Not only is this the brightest glow of any filament on the market, but it can continue glowing even 6 or 8 hours after light exposure. This makes it perfect for everything from emergency exit signage, high visibility or safety gear, and more. And as someone who suffers from a lot of construction-related power outages here at the studio, I can appreciate that. If you appreciate all the work, research, and test printing that went into this video, then please don't forget to preheat the subscribe and like buttons. And if you like videos like this, do make sure to check out the other videos in this series using the playlist here. I think we've already done like 5 or 6 of them, and they're always some of our top performers. That's all for this week, but I'll see all of you on the next layer.